Alright, CNT140, we're looking at Chapter 14 on fiber optic testing. Now, just a quick little heads up on this chapter. I'm treating this really as just kind of a overview for familiarity's sake. We have limited ability to do any of these tests in our lab, so we'll just at least make ourselves familiar with the meters and the kinds of things they're talking about when we're testing fiber optic cable. Alrighty. The introduction, they give us a quick overview of some different test parameters that gets done on fiber optic and the different meters that's getting used. The big ones they mention here are your fiber optic power meter, which we'll touch on, and also your OTDR, optical time domain reflectometer. We'll touch on that one a little bit too. Alright, just to kind of get them right out in the open in front, as it says in the beginning of the chapter, here is some samples of fiber optic power meters. This is their light source end. This is the end that actually is measuring the signal strength, if you will, the light signal strength. The other one they talk about is your OTDR, optical time domain reflectometer. This looks very much like the meter we have in the lab. It just has an adapter on for fiber optic connection. So this is going to do the same kinds of things on fiber optic cable that we've done with copper cable. In this case, looking at distances, looking at where particular problems are in the cable. They also mention towards the end of the chapter a visual fault locator. This is actually handy. It's almost like a laser light source that attaches onto your fiber, and it'll send a very strong laser light source to the fiber, and if it comes out the end without any issues, we know the fiber's in pretty good shape. If it gets partway through the cable and starts lighting up the jacket, we know there is microfractures, breaks, or something at that point in the fiber. So it allows you to locate if you are having a problem, maybe visually where it is, to know how to deal with that fiber. And they also mention in the chapter, when they start talking about connectors, about your inspection microscope. This is actually a microscope that attaches onto your fiber cable connector here and allows you to look at the fiber end up close magnifying to know whether you have dirt, chipping, epoxy residue, whatever it is on your connector end, to know whether the connector itself is in good shape, good working order. Okay, first thing mentioned is your standard test procedures. There's international standards, and in the US, the standard that we focus on is our ANSI TIA. ANSI TIA 568C3 talks about the relevant fiber optic data that we would need to know. As we look through, they talk about connectors and identification, that sort of thing, but they also talk about optical loss on connectors and splices and that sort of thing. Those would be some values that we would need to know if we're testing fiber links or fiber connections. So 568C3 about optical fiber. One of the first tests they mention is measuring optical power. What happens is if we zoom back here with our power meter, you set a light source on one end of the fiber cable or fiber run, and the other end measures some value on that signal that's received on the other end. So with our fiber optic power, it's a basis for loss measurement. So if we send in a known signal of, let's just say, signal strength 10, and it comes out the other end 9, we know there's just a little bit of loss. If it comes out the other end 4, we know there's significant loss. That's the idea. That's the basis for your loss measurement. Measured with specialized light meter, yep, your fiber optic power meter. And it actually has interfaces for the fiber connectors, and it typically measures at 850, 1300, and 1550. Your multi-mode and then your single mode light sources, if you will. And again, here's your fiber optic power meter. It's two different examples, so you can just kind of visualize what you're seeing there. They talk about some different loss tests that can be done, and there's also fiber optic test procedure 171, and there's another one they mentioned a little bit later. You launch a light from a source of a known power output, and the other end, the meter end, measures the power loss. You set the meter itself on either LED or laser, depending on the wavelength of light you're using. Obviously, it has different connectors, different connector ends for the different types of cables you might be testing, and you choose the wavelength for the particular type of fiber you're testing. So if you're testing multi-mode, and I think I have this on the next page, multi-mode, it's going to test at 850 and 1300. If you're at single mode, it'll test at 1310 and potentially 1550 if you have really long cable run. The reference cables must match the size and have mating connectors and all that, so if I'm testing a multimode cable run that is 50-125 multimode fiber, then my cables attaching to it need to be 50-125 multimode fiber. That's what they're getting at. And your launch cables must be high quality. Basically, the meter cables themselves need to be high quality for this test to be any kind of accurate. Then they show you two different test procedures, the fiber optic testing procedure 171 and 14, and they show you here, and I kind of put a little note down here at the bottom to try to get you to thinking this would be the kind of test you do on maybe a patch cable. This is your patch cable you're trying to test. And over here, this would be the kind of test you would do on an installed cable run, if you will. Just to give you an idea of, they have two different parameters, two different test procedures to allow for different types of cables that you would be testing. Just to kind of give you an idea. And then they talk about different ways you can calibrate the meter, method B, A, and C, to calibrate the meter for basically a known value, and then when you test the cable, it'll know, okay, well, it's supposed to be 20, and I'm now getting 10. I know there's X amount of loss. They talk about method B, A, and C, different ways to calibrate the meter. Testing multimode cables, they mention using a mandrel test. With this one here, you actually wrap the fiber cable around a mandrel, and they show you, or they tell you here, that filters out the higher order modes to create a predictable light source. It's going to create concentrate the light towards the center of the core. And actually, I have, if you bear with me a second, if I go back up here to a earlier picture, I actually see on the OTDR, you see the mandrel right here. This is what they're talking about, wrapping the multimode cable around the mandrel. That's what that's showing you in that picture. That'd be the mandrel test. Okay. I've seen articles where they still use this. I've seen articles where they're phasing this out. So it's something that can just kind of be familiar. If you see that, you have an understanding of what that is testing, or what that is doing, and what test that's performing. With multimode, they talk about the size of the mandrel and the type of fiber that you would be testing. The measurement of loss for our signal is measured in decibels. And decibels is a logarithmic scale. You can almost think of that as exponential, if you will. And our measurement is done in decibels, dB, down here. And what they mean by this being a logarithmic, or I'm going to inject the word exponential scale, is if I have a decibel measurement of 10, the power ratio equivalent of that is basically 10. Meanwhile, if I have a decibel rating of 20, it's really 10 times 10, which would be like 100. And 30, as you see here, is really 10 times 10 times 10, which is 1,000. So the value goes up exponentially. That's something just to be aware of. Our measurements being in decibels, things go up exponentially, either in gain power or loss power, if you will. So what should we expect for, what kind of loss should we expect when we are testing fiber cables? The chart in the book gives you a quick breakdown of connector loss and multimode. I might expect somewhere around 0.5 or 0.75 decibels for a connector. I'm going to use the far right column over here, the T568. So for a connector on multimode, I might expect just under a decibel, 0.75 decibels. Meanwhile, if I have a splice where I'm actually splicing two pieces of fiber together, I might expect about a 0.3 decibel loss, about half that. Those are some numbers just kind of keep in the back of your brain. And I pulled up our standard just to reference as I look at it. Our 568C3 standard says that the insertion loss for a fusion splice is 0.3 decibels. That's the maximum allowed insertion loss. Meanwhile, a connector that you would be connecting onto the end of fiber, expected loss, maximum loss is 0.75 decibels. So just, again, keep those in the back of your brain as you would be testing fiber. Those would be the values, kind of the max values you'd be seeing. So this very small numbers of loss that should be here for that signal to get through. The next thing they mention is our inspection scope. Again, after you have a termination, which we'll talk about the next chapter, one of the things that should be done is checking the end of the fiber to see if it looks polished well, clear, free of debris, free of epoxy, that sort of thing. And that's done through our inspection scope. right here, this guy right here. Now, heads up warning on this one, you never connect this to a fiber unless you know the other end does not have a light source on, because that would be concentrating that possibly laser light source into your eye and doing eye damage. So just kind of a little heads up on that one. But I connect my fiber, and there's actually a light source in here that's designed to bring kind of the light from the side and then into the that I can see the end of the connector, and I should be seeing this nice clean connection. As I magnify over here, I start seeing things like epoxy and chips and that sort of thing. I would know that this is a bad end, possibly the source of my insertion loss or my attenuation that I have on my cable. Another test that I can use to try to narrow down where I'm having loss is my OTDR, my optical time domain reflectometer. If you remember when we were doing copper cable testing, my TDR is the meter that measured my distance of my cable, and that would also help me determine if I had a problem in my cable. Example, you installed your cable in the room, we put the little wire mat meter on, and it told us the cable length. Let's just say it was 34 meters. I come back later, a month or a year later, and I test the cable run, and it comes up 14 meters. I know I have a problem at roughly 14 meters away from me, a cut, a disconnection, something is wrong. So my plain old copper TDR is helping me narrow down where the problem area is. The same thing is going to be true with my OTDR. It works on the principle of looking at the back scattered light, how much light is being scattered and sent back to the source. Obviously, the more there is, the more potential problem I might have at a specific distance. Okay, that's done with my OTDR here. They give you two different examples here that I connect my fiber cable right into. Okay, and that is going to run a test on my cable run where it's going to send a light source into our cable and measure the amount of light coming back, how much light is being bounced back. And this ends up making a graph like we were used to seeing even on our copper cable runs, where I send a light source out to the other end of the cable, and it's going to graph for me little anomalies that are happening. A little bit of light is going to scatter off a splice. A lot of light is going to scatter off of a connector, and then I'm going to have basically infinite loss at the end of a cable run. And it's going to be able to determine from the light scattering coming back where these anomalies are and give you distances to them. So an actual meter result might look like this. Again, this, think of our TDR that we used before. We scanned our cable run, saved it, downloaded the results, printed it out, and got a little graph. Well, the OTDR is going to work on the same principle. Here it's sending a light signal in, and at blah distance, we'd have to zoom in and see the distances down here. We get a little teeny blip where two fibers were spliced together. As it keeps going, it gets a large blip here where it happens to be a connector. Maybe that is the other end of the cable run, and that would give us an idea of the distance of our cable run, or if it's supposed to be longer, where the particular problem is. Maybe there was a break or something of that nature. And then we have basically unlimited loss out here. That's what we're seeing here. That is truly the end of the cable then right there. So there, with my OTDR, that's the kind of thing I'm getting, and then I can start interpreting from that particular problems of splices, connectors, ends, that sort of thing. And I compare that to what I know should be in the cable run, and that's going to help me find particular problems in my cable run. Here they give us a couple parameters on this and setting this up. Should be connected to the launch cable, adequate length. Yep, they even give you some guidelines here about the launch cable needs to be significant length. That way it is not, the light source itself has time for it to actually get into the cable and then actually reflect back. If this were too short, everything would be happening too quick and it wouldn't be able to determine distance of things. So my launch cables and my cables to the other end need to be of adequate length for that. And then they talk us here about shortest pulse and range as long as the cable, wavelength of the sword. Yes, there are some things that have to be set correctly for this to work, and that's what they're giving you some guidelines here on. And here they even give you some limitations. Distance limitation by the pulse width, crosstalk and reflection, saturate receiver, yep. Limitability, resolving too closely spaced features, yeah. If I have a splice and a connector too close together, it's not going to be able to interpret them well. And the OTDR attenuation measurements depend on the backscatter coefficient, how much of that light is getting scattered back and how much the receiver is able to pick up on that. Okay, and our visual fault locator, this guy here, is basically a light source that I'm going to send into my copper cable, or excuse me, my fiber cable, and if it goes the whole way through and out the other end, we're in good shape. If not, we know where the break